Okay guys, just a short video. Some things are easier drawn than typed out in text. So this is going to be a real fun experiment. You you are going to throw in, and this is important to realize, you will be chucking in real living organisms into your broth or medium that you prepare. Basically what will happen, there'll be sugar in them. There might be some yeast extract. If it has a yellow color, there'll be yeast extract. We'll get to what yeast extract is just now. And then these organisms will be requiring energy. Okay, how do they make energy? They make energy by making ethanol, but as you make ethanol, you make CO2 as well. So basically what's going to happen is they're going to produce CO2, and the CO2 is going to flow through the tube. We're going to have a little device that's just to control the liquid level in that upside down pipette. And what will happen is gas will form. Gas will form at a certain rate, and it will displace, and I can draw on here, it will only displace this liquid level. So it's all about getting the delta V over delta T, which will be the RCO2 rate. This is what it's about, people. So it is about how fast your level in your pipette is dropping, because that will be telling you how fast the organisms in the mixture are producing ethanol, or if more effectively, how fast they are producing energy for themselves. So just before we get on the measurements, please note there's a difference between yeast extract and yeast. So the yeast extract is that yellow powder that you're going to prepare. Some of you, those doing maintenance experiments, won't be having this yellow powder, because what this yellow powder is, it's not alive. It is derived from dead yeast cells, but it is what we had in CBI, effectively you can say your nitrogen source. It's not ammonia, it's a complex nitrogen containing molecules, but it's really what the organism requires to grow. Okay, please don't confuse that with the yeast itself. If you go to that incubator, the temperature controlled little room at 35 degrees Celsius, you'll get bottles with green caps and bottles with blue caps. You will see that the color of the inoculum, we call it the inoculum because what's in the inoculum is physically cells itself. Okay, so there's that yeast cell, and maybe it's already starting to form a little baby. That little bottle that you take out contains the yeast. Okay, don't confuse that with yeast extract. That's the living material. And really, at the point in time that you add, and please note, make sure to take a green cap if you do a growth experiment and a blue cap if you do a maintenance experiment. That's going to be chucked into your little fermentation vessel. And when you chuck that in, that is time 0. And that's when you start monitoring your reaction. Okay, so let's just talk a little bit about measuring the liquid level in the pipette tube. So what's going to happen is liquid is going to be pushed down by CO2 forming in the fermenter, and it's really all about the rate of this liquid level dropping, because that will tell you how fast they are producing energy from sugar. Okay, so if you have a growth experiment, you might find that your volumetric rates, remember it's all about the delta V divided by the delta T, they can go in excess of 10 milliliters per minute. Okay, so basically if you've got a 50 milliliter pipette, in 5 minutes the whole volume will be displaced. So when you do this measurement, it's very important to take as big a volume as possible. So have some virtual marks on your pipette. You know, if you running at as high as 10 milliliters per minute, you know, try and make that volume as big as possible. Let's say we can make this volume to be a total of 40 milliliters. And what now will happen is you will wait for the level to drop. So you will wait for this level to drop up to the point where you start your stopwatch, and then try and displace as big a volume as possible, and then you will stop your stopwatch when you reach the second mark. Okay, so all you have to do now is to say, we know what the volume is. The delta V was kind of set beforehand for maybe 40 milliliters, and the delta T, because that will give you your rate, will just be, let's say, for example, 4 minutes if you had a rate of 10 milliliters per minute. So this rate is something that you want to constantly monitor, okay? And you want to actually report quite a few of these rates, okay? Lastly, if you're doing a maintenance experiment, now if you do a maintenance experiment, you will see that your rates is going to be smaller than 2.5 milliliters per minute, and you will note that it drops kind of not always at an even speed, okay? So when the rate is very slow, we're going to do an accumulative measurement. An accumulative measurement is really going to be taking a few volume readings against time. So at some arbitrary point, you will decide that a certain mark on your pipette will represent 0, and then you'll have time increments that you define yourself, okay? Now at these time increments, you will measure the delta in volume, okay? So at this first point we had over here, we would say that the volume, that the delta V is 0, and then you will basically just get the change in volume over time. So this will be delta V1, delta V2. Delta V2 will be the difference between time 2 and time 3. And then you want to have a cumulative volume, which is really just adding delta V1 to delta V2. Over here, you keep on adding all the volumes, all the delta V's. So you keep on with this, and you end up with a accumulative volume. So this will be volume accumulative against the time increments that you've placed. Typically, you will make this to be from year to year, maybe 30 minutes or so, and you will find, or you should get a line that looks like a pretty straight line, okay? So after you've plotted the total volume displaced over the time increments that you've placed, you now just want to do a linear fit, because we expect a constant rate. So you're going to do a linear fit on the data, and that slope of that linear fit will be the best approximation for the average rate that you are getting over the whole time span, okay? So if your rates are slow, remember, we want to work with cumulative plots by taking the total displaced volume and plotting that against time. Okay, that's it.